Welcome everybody to my talk, Testing Templates, Testing Tests. Let's see how this works. So this talk is about improving test methodology step by step. Okay, first about the contents of this talk. We'll talk a bit about me, small preface. I'll explain how to test tests and how to do it in a structured way. We'll talk about compile and runtime variations, measurements, and my new idea, adversarial testing. So, about me. So, what brought me to this topic was I've studied both mathematics and computer science, and I'm kind of switching back and forth through my career, through my education between those topics. Started actually with computer science, but I thought mathematics is very interesting, so studied that, but my work is really more in the computer science area. When I'm not doing any of that, I found a new hobby is like a ham radio operation, which is also very fine. You get to communicate with people all over the world. If you're interested, ask me. I can tell you a lot about that because I'm also a trainer. If I'm not even doing that, I'm playing the piano. Not very good, but it's okay. Okay, so what about Bosch? Some people don't know that, so we're always told to give the people background. Some people really don't know Bosch outside of Germany. It's a technology company. We're privately owned, basically. Through a foundation, so that means it gives us more freedom. We're not chasing so much our stock rates or something, we can have really a big research center where many people are doing fundamental research. I'm coming from the automotive area. Specifically, I'm doing radar and video sensor development, and I have a basic template library that is used in all of these devices. There are other areas which power tools you might know. Home appliances is something that people tend to know. But as you see, all of that involves many embedded applications. So I will naturally focus more on these embedded applications. We use all kinds of programming languages. We use C, we use C++, but we're so big, we basically use every language that there is. Okay, so what I will present here is I will take some topics and examples from my work. And that is really the C++ template-based library, which has some special containers that we use and some mathematical functions. I will talk about unit tests, specifically because that make most sense in our use case. But I think some of those concepts I will present might be also relevant or usable in other contexts. For the presentation, I will use Google Test because that's what we use, and I think it should be known to many of you. So I will try to explain the things that might not be known. I will also not claim that this is some kind of research or research overview. It's just like a practitioner's view from my side and some opinions from my side. So I don't think anything is radically new from the idea, but the thing how I used it might be new. And some of those things we tested, we used them in production, but the newer ones we're just starting. Okay, so how do we go about that? What can we do? Let's say I want to test a template function. I have a template function, something very simple, square function, but as a template, taking a template. What we're using is Google Test here. So it has these handy test macros. You just put some expectations in there. You can give some names, the name for the test, which is important. Then you say, okay, so we test some non-zero inputs. Okay, If we square 1, we get 1. If we square 2, we get 4. If we square 10, we get 100. And we put this in a different section. Test 0 is something with 0. Great. Right. So this, if you use Google Test, you basically compile it. It will run through. It would say, yeah, it's great. Your expectations are good. You're good to go. But looking at these tests, you have to think, come on, is that everything? That seems very superficial, right? So integer has most oftentimes it has like 32 bits. I'm just testing 4 cases. I mean, that's probably not enough. But as a template function even, so it's not enough to think about ints. You have to think about all kinds of other data types that might go in there, that might be bigger even. So, and if you even consider all the built-in types, you still have the types that the user will provide. So because the type is open, everybody could put everything in there that has multiplication operator. Right now, let's look at class templates. Class templates, yeah, you can also put them in this Google test framework. You just write a test. You just take your own vector implementation. Then you say, okay, I create a new vector. Then I expect it to be true. Size must be 0. Okay, nice. I push back 1 element. Then I say, okay, now it's not empty anymore. The size is 1. Okay. The front element is 1. The back element is 1. Okay, cool. I erase something. I erase the first element. Okay, then it's empty again. Yeah, great. And then I expect the size to be 0. Okay, so I did a lot of these macros and you can follow that through. It makes sense. And you see this is the result from on the right side. You see the result from Google Test. So that's how the output looks like. You get, yay, I'm running this. It's okay, it passed, and I get a nice summary. So that's fine, right? No. Okay, so if you look at the code, which function did we test actually? Did we test the constructor? Did we test the empty? Did we test the size, the pushback? I'm not so sure. So again, here the question, what about the other types? So we have the int there. Yeah, that works with one value. Okay, cool. But just one pushback, but that doesn't seem very comprehensive. And so where would I put that? So obviously, StudVect has more methods. So would I put this in the same test? So it will get longer and longer, and I have like several hundred lines of code. Nah, I don't think so. That's a good way to extend that. So another thing we have to take care about when testing. Let's have a look at this function, template function. So okay, we have a template function here. That takes some kind of sequence, some iterators. Okay, nice. Then, okay, it takes the first element somehow, right? Then there's, it starts, it goes to the end, right? And it increments the first element and stores it back. Okay, we can do that. So, and now we write a test. Okay, I have vector, it's unsorted. I just call this sort sequence. Yeah, and I expect true. It's sorted, and what do you think? It's sorted. Yeah, yeah. So what would be the reaction? So okay, so you say, yeah, it's sorting. So is it sorting? No, that's not sorting. So, but really, what we find here is naming really matters. The naming is really, really important. And why is that? Because the requirements matter. So the only thing that gave us the requirements here for this function is basically the name. And the name implied something with sorting. So let's forget the name for a second. I just present new requirements. I have these requirements. The function sort sequence shall generate an ascending sequence in the given range, where the generated sequence starts with the first element of the given range, and the following elements are incrementally incremented by the value 1 each. Okay, that sounds more like it. It seems to match the code we saw earlier. And so what's the point here? So we might assume if we look at the code is wrong. But why is that? Because we had this implicit assumption about the sorting function that is still sort something, which is not doing that in the way that we want. So really, what is important to have some kind of specification. This might sometimes be implied by the function name or the context, but this you really have to be careful when testing, really be aware of the implicit assumption and make them explicit if possible. So if something is called sort, it should not change some elements, create some elements that were not there previously. And so the takeaway here is, for me, every program is correct to some specification. So if you have no specification, how can you say this is wrong? That's really something they have to remember. So some people say, okay, this function is a bug. Yeah, but according to which specification? Sometimes people forget that. I know it's hard. It's really inconvenient to say, okay, please write a specification for this function. But without specification, I cannot really test against anything. Okay, just first break now. Okay, what have we seen now? It's possible to test templated functions and class templates, but it's really clear we have to know what we're testing against, what we want to test. So that we have to have some requirements there. We do have to think about the runtime data. So we have some data that we want to test against. We have to know where this is coming from and which one is the data. And also we have to somehow define which variations in the compile time we have. And by that, I mean mostly the different types that I put into these templates. So for me, this approach, which Google Test, if you open Google Test documentation, it will blurt you out. There's many examples how to do that. Doesn't seem really good for testing template functions and templated classes. Therefore, we need something better. And it's certainly not a good way just to do copy replace or some templating engine generating the tests. That doesn't make sense for me. So it would be cool to have like a cool structure where I can see which is the data, which is the types that I'm testing against. But really what I want to know is, when is the testing done? When is my test really good enough that I can go home and say, okay, this code has been tested enough so that we can put this in cars that drive on the street. Okay, so I have some requirements towards my testing. And what would that be? It should be easy to generalize. So many people say, code tests, it just writes only once code, you write them down and then it's fine, and then you go home, you never touch tests again. That's a philosophy, but not mine. So I want this to be easy to generalize. I don't want to use magic numbers everywhere. Next requirement for me would be, they should be easy to extend. So once I have set up my test, if I come up with different data or different types, it should be really basically just one line I have to add somewhere, and this will be in it. I don't have to copy everything around and change that. And as a reviewer, I also want to see really what is tested, which types are tested, and with which values are they tested. Okay, so let's see if we can achieve that. So I was lying a little bit maybe. Of course, there are templated tests in Google Test. You can do that. So what you need is some basic, you need a test class, a template test class actually. So you can derive that from testing test, which is we see here. Then we define a list of types with testing types that we want to test with. Okay, now that's closer to what I need. We define something called a test suite, basic test types, and this is assigned somehow to these basic types. Then you have a different macro. If you remember, we've seen this test macro, and now it's type test, so something with types. And then you have to look here. So what we put here is this type param, and where is this coming from? yeah, it turns out it's part of this macro magic here. So you have to know and remember, okay, this type param is like magically appearing from this macro, and you use that. Okay, I can deal with that probably. And then just I make a simple test. Okay, I have some, just here I want to test the construction, so I just make vector with 3 elements, cast that to the type I want to use. And here's another test where I just have a similar setup, and I just say, okay, it's just access the element and accept it and see what's in there. That's possible. So what will this do? Basically, here, all these are all also implicitly template classes that get instantiated somehow with all these different types that are above. So I would say this solves my part of my problem, that I want to have different types tested. So in one dimension, we're kind of clear. Yeah, but what's the problem here? There's even more macros, right? So there was this macro for testing, where I can't live with that. But I have like 2 different kinds of macros I have to use, and somehow they don't, the structure there is not so, not like how I would need it. So it's really hard to customize. And if you have different types you want to test, you have to have a new test suite. And sometimes we found that if you use these macros and you have some namespace where you put it, you get into trouble, because the macros, of course, don't respect namespaces. Then there's this type param, which appears out of nowhere, and you have to deal with that. And you can have only one parameter. So this typed tests will always have this one type parameter, and there's really no way to change that. So you have to wrap it and then unwrap it. I mean, that's all possible, but it looks awful. And another problem we ran into was if you do it like that, we have problems with modularity and extensibility. So what do I mean with that? So our idea is, as we are a very basic template library, we cannot know all the types that the users will use. So we can ship our tests to our users, and we can say, hey, look, we have tests here. Just put your types in there, and you can run the tests and see if there's some incompatibility, right? But that's not possible with this approach, because here we have to know all the types that we want to test beforehand, right? So we cannot easily separate that, the way the structure of the macros is working. And still, it doesn't solve my runtime variation stuff. So you've seen the setup is everything all still in the same class. Okay, so what do we do? So we said, yeah, okay, it's possible to do that with macros, but actually they're not adding much value. So they make it a bit nicer to write it down. You can kind of save some lines of code, but in the end, yes, so just some minor infrastructure stuff you need, and you can make it work with just regular classes, template classes. And we can just use we always anyway have to derive from this testing base class. Just do that as we did before. And we just implement everything else that we need, what is provided by the macros by ourselves, and we can see how this works out. And hopefully we have more control over these instantiations. So this is how it looks like. So it's pretty similar, but I put this in namespace so that our tests are pretty, they're taken care of. It's in the namespace, so we don't get name clashes with different types. Then it looks, basically the code is the same. So what we have to consider here is what the macro is doing for us usually is it's basically you have to provide a virtual function. So it's all actually a class. You have to implement this test body, and then you have basically the same code as before. So it's a bit more wordy, but we have much more control here. So here we see, okay, I can give 2 parameters, and nobody stops me from that. And I used here the type names, the names of the parameters. I can choose them. I can use whatever I want. And it's not so much more to write, okay? So But then it's unfortunately it's not finished. So the stuff that we're seeing now here is the replacement of this test suite thingy. So what do we do here? We have to instantiate that. And this is where we have to kind of re-implement some of the stuff that Google Test is doing in these macros. So we just made a template that can instantiate multiple times. So we have here, we just manually instantiate that. And so we could have done it the same way as Google Test, but then we would have so just you pass it a type list, basically. It gets instantiated with a test class, but that will make problems. So here we decided just to put this explicitly there, then you see what's happening. And then here you have also the possibility to have multiple parameters in the instantiations, which is difficult if you have like just a simple test macro. Okay, great. Yeah, so we're going for that approach, and it's used successfully for us. So we can group the instances like ever we want. We can put them in different files if they get too big on our embedded platforms. We have really the total freedom to separate them, and we can also say, oh, dear customer, please run our tests with your classes that you use them with. So they can test their classes with our containers. And you really have a complete freedom. You can do everything in the template space that you want with this approach. And of course, because it's just the infrastructure we've seen is basically just pure C++. There's no magic stuff happening in macros, just in the expected macros. We can use basically whatever we want as namespaces. Okay, so just next point was the data. So the usual solution to having different data is, okay, I have this test class. We didn't use that correctly. So the idea is classically, okay, all the data that you need for your tests, put them in the fixture. So this is a base class of your tests. And so everything you have there, you can reuse them in all these tests. And it makes sense. So it's just so here I just make it. It's public, just a structure. I put four vectors in it that I want to test. Different constructors, and I try to really explain what this is supposed to be. So the one's supposed to be empty. The next one is just one element, and then I just have 100 copies of one, and then I have like 4 primes because have some variety would be nice in the values. Okay, but yeah, what's the problem with fixtures? Yeah, one problem is it works in many cases, but there are some cases where it's really not so nice. So consider you want to test a copy or move constructor, and you have these examples. Then you somehow want to test to move, to copy every instance to the other one, right? To see if this works. And if you do it manually, if you write it just down, I'm pretty sure you will forget some case. Or if you change a test later, you will never find it. So our idea was if like move constructors, copy constructors that you want to test, especially the ones you've written yourself, also binary operators. You need 2 sets of items. So that's in those cases it would be very awkward to test it. And also there's a kind of strong coupling between the instance and the test data. So what we said, okay, it might be easier if we just don't couple the test with the data generation too much. And so we said, let's move it to another special class. Okay, and this is how it looks like. Basically, the idea is we can take a member class and we call it equivalence classes. And usually we call it the same way every time, just equivalence classes. And then there's the classes are inside in some kind of, could be an array, could be vector. And then the pattern, how it looks like when we run this test is basically we run through all the classes. We just have a for loop, and we just take every item out, and we do the testing on that. Okay, so where's the advantage for that? I mean, it's not much difference to the one before. But the idea is here really to make really sure the test class is a test class and the equivalence classes I'm dealing with are equivalence classes. So I think it is important to distinguish between the test infrastructure and the data that you're dealing with. And you could also pull this out if you think it's not good to have a member. If it's in the namespace, it usually the context is quite clear what this is used for. And a big advantage, you can instantiate multiple times. So many times you also need to have like different sets of these copies of these equivalence classes. Also, you have to test const methods. And how do you get a const element? You can do const cast and const references, blah, blah. But you can just take the whole thing, instantiate it at const, and you got it. Yeah, so again, I told about the alternatives. You could do it in vector or some other container that you like. And so also we don't have to instantiate it if we don't need it. So if we not need it for some specific test, you can skip it. Also because we have it as a separate class, it will not be part of the test infrastructure. So everything happens on the stack. So for us, it's important to have some good control where the data is located. Yeah. Okay. So and this is okay. I think this is the way how this is the setup would look like here. So we have basically the same examples here, but we just put them in this equivalence class structure so that the difference is not so big on this side, but here we see now a complete test for the copy assignment operator of our class, which might have all kinds of pointers in it, and you can do, might break in different ways. So if we test it here, so what we do have is a double loop. The outer one is the const one. We just take that as the source. We take a set of, another set of equivalence classes. We instantiate that. We do it inside of the loop, so we have a fresh copy there. And then we overwrite the destination every time with the source, and of course we expect the size and the quality there. And so whatever, if we change or extend the set of our equivalence classes, it gets automatically tested. We don't have to touch anything, and we get like both sides of the assignments, and we don't have to think about that. So yeah, and of course we have to instantiate it, and we can put all the types that we want, but just for completeness. Okay, we use that a lot, and there are some variations. You might put that really out. I told that. But what you typically have is this equivalence class has just the default constructor where you do all the setup. What we sometimes found is it might be helpful to have a templated constructor if you pass in some functor or whatever to make it more customized. You can do that, of course. And one thing, what you typically always have is some kind of iteration possibility so that you can iterate over all your equivalence classes. Sometimes you also do like aliases for some members of these classes where we say, okay, this is somehow really special. We want to handle that specially, or we want to have it a good name for that. So you can just add a reference alias member. And what you can do is you can do some kind of minimal checks also in the constructor, just to make sure that you didn't end up with the wrong construction or something. But really, the task of the equivalence classes is really to set the stage and make it ready for the tests that can go over them in a structured way. Okay. So the advantage of this is we really have a clear class that is responsible for all the runtime variations that we have. So everything that's created at runtime is done here. We can have multiple instantiations, and the test code is kind of automatically very abstract if you do it like that, because the only thing you can do is, okay, I have some instance here, and now I have to test some property or some requirement. And this clearly separates the test data and the test code. And we just use like standard language tricks. There's nothing special here. no macros involved. Also, we can instantiate, like if we want to have expected results for some method calls, we can just not instantiate like some object under test, but also some expected results for some functions. Sometimes what we also do is, if the test is rather complicated and if you want to know what equivalence class is failing, that we also put the name there. So if you have like a failure, that you get a good name for the output. Of course, there are disadvantages. So we have another level of indirection, adds another line of code at least. And the fixtures, if you're working with fixtures, it's kind of hard to get away with that, and probably you're already dealing with it okay. And that also is, it's not always clear why this is better. So I've shown a case where I think it's better, but maybe there are other ways to work around that. It's hard to see. And it's not very self-descriptive sometimes, so you have to get used to that a bit. And another thing that people say is problematic, that sometimes you have to do runtime decisions. So if it's an empty vector, which you don't know because you're just getting a list of elements there, you don't know if it's empty, so you have to have a runtime check inside of your test. And this is, some people don't like it. They say, okay, it should be all one on go, and no special handling in tests. I'm rather pragmatic. For me, that's kind of okay, and there are some ways around that. If you put some like template parameter on the constructor of the equivalence classes, you can just select if you want to have empty containers or not. Okay. Right. So what do we have here? Another limitation here that we run into. Coming more to the mathematical stuff here. Let's say we want to test some addition function. Okay, it's unfortunately not on the slide anymore, but you can think how it looks like. It's just adding two integers. Here we also have like a double loop to test. Let's say we test all the combinations, right? So we want to be really thorough, complete, and we just add everything. And I mean, there's multiple problems here, undefined behavior, blah, blah. But anyhow, so if we run this, and if we run this in Compiler Explorer, okay, it gets killed. Okay, why? Int has like 4 billion possibilities. Okay, we're just doing half of them, but okay. It will basically never finish. Whatever computer you have, if you have one that really can finish this loop, you're really, really lucky, but I doubt it. Here it gets killed, like I think about 15 seconds in, and it doesn't make sense. So even if we can write code to test it, it will never finish. So there are some exceptions. If your data type is really small, it will finish. Okay, so like 16-bit integers, okay, go. But like everything that has like a total bit count of more than 32-bit is probably too much. So that means if we cannot test even a simple addition, we cannot test everything. That's impossible. And so that leaves us with incomplete tests, and with incomplete tests we cannot prove that it's correct. Okay, that's bad. But let's say we have enough compute power, and we just buy more servers. We put it all in the cloud, and we buy Amazon and let them do the tests. Even if we could do that, it might still not be a good idea, right? So what are we testing here? Addition. Oh, do we really want to test that? So it will cost us a lot, and like we produce a lot of carbon dioxide, and we don't really want to do that. And so, especially for unit tests, we say, okay, if it takes really long, it shouldn't be unit test. Okay. Now, next point. So we have this structure of equivalence classes. So we have neatly enumerated all the classes that we want to test. And so how do we choose them? So I've shown that for my vector class. So we have to decide which are the equivalence classes. So of course, the empty one should be in. Then we have just one element, which is also a good equivalence class, and then many elements. And maybe we want to define many elements to be a reasonable size. I wouldn't take 1 million, but maybe some odd number or any larger number. And we can say, okay, this is for our testing area, that would be the standard number to use, okay? But also, what also is equivalence classes is like combination of parameters to pass through the function. So we could have different kinds of iterators we're using, and then also we have the equivalence class for the object state, which we defined before, and then for the iterators, of course, we can have the begin iterator, end iterator, something in the middle, and that would be another set of equivalence class for the iterator. And of course, we can combine them both. We have the state for the vector and for the iterators, and we will combine them so we can test everything. So what I try to avoid is really putting everything in the compile time. You could probably do all of that also as a compile time construction, but we really, if it's possible to construct these equivalence classes at runtime, it should really do that. Because constructing something and also variations at the runtime is really cheap. That's what we do. We had some different numbers here. What's also important if you're dealing with some kind of mathematical functions or functions taking float numbers, there are these like special float values that not everybody's aware of, and they have really, really funny properties, especially the not a number. That's a topic for another talk. But if you're testing and you want to be thorough, these should be good candidates for your equivalence classes. Okay, now coming back to the container area. So of course, if you have a container, so it should work for the primitive types. I should have a bunch of those. So you will also get different alignments. You you will check for forced alignments. You want to check if it works with const qualified types, if that's a thing. And also with special member functions and deleted member functions. So you might have move-only types. So this is what our users are starting to discover. So, but not all of our containers are really supporting that. So that's a good thing to put in your tests so you can be sure. And then there are even more crazy users, maybe that it's not even movable and it's not copyable, but I still want it in a container. And you say, okay, right. So this is, and there might be other combinations that you want to look at. So also, again, for mathematical functions, you should try also all the signed types that you can do arithmetic with, the floating types that you support, and for non-primitive math objects, like if you have something, vectors, matrices, and unit types. So that is something that you want to take into account if your templates allow for that, okay? So because those often have overloaded operators plus, and so these are very prone to also appear inside of such algorithms. Okay. Yeah, now we have, there's a question.
Yeah, so I want to ask, what's the motivation behind testing types with different alignments?
Sorry?
What is the motivation behind testing types with different alignments?
Yeah, so we had issues if we have containers with differently aligned types. The alignment rules are not very strict, and some strange platforms have some strange rules. So this can break on special platforms if you put in, also it can break some assumptions at least on some platforms if the alignment type, if you put values there with special alignments. So we said we want to test that. Therefore, it's on this list. Just we found out that we need to test that. And of course, alignments are different on different platforms. So, and this can have different consequences then, of course, also for the test.
Thank you.
Okay, yeah, but now we have a way to define runtime variations. We have also the type level variations, but of course this multiplies, right? So it's getting more, And so if you do it like this, it's quite easy to generate code that generates lots of generate code that tests really a lot, but it might really be too much because we just not having just the runtime dimension, but also the type dimension. So everything is compiled again with different type, and it runs again. So we really have to be careful here. The method is quite powerful, but again, it might be too powerful. So really have to consider what are you testing. So the example that I gave is like, yeah, shouldn't do that, like testing addition. But it's very unlikely that this will yield anything in your context. So it's that's basically testing both your compiler and your hardware. That doesn't really make sense. But if you have a function that uses a known function, that might really be worth testing. So you should really concentrate on that and really be careful and considerate with the selection of both your equivalence classes and with your types that you test. Okay, so another step back. So I say break. Let's drink some water. Okay, so now where are we? So I would say this seems more structured to me, so that's nice. We have clearly defined where the runtime variation is going and where the compile time variation is going. So are we finished yet? Or am I finished yet? No, not really. So there's even much more stuff going on. Okay, we cannot test everything. Okay, that was somehow clear, but it's with templates, it's really getting worse. And we have to be careful not to test too much. So we have kind of conflicting goals here. So we want to be done quickly, and we also want to test as much as possible. This leaves us in a very bad place, right? So we have to release good software, but we have no way of saying, okay, that seems reasonable now. I can stop now. Okay, so where does it leave us? What are people doing? They turn to coverage. Coverage, let's do coverage. And if we have coverage, everything is fine. If we have 100% coverage, we can go home and everything is fine. Yeah, okay, so what's coverage for those who don't know? There are tools out there that just can measure which code paths are taken. There's some instrumentation going on, and you get nice outputs, which statements or lines have been reached. Okay, cool tool. So what they do is they can output some percentage number of the lines of code that have been covered. So the idea is you reach 100% of code. And it's a cool tool. You see, okay, my test is reached there. Oh, I didn't test that case. Totally useful. But the thing is, if management sees that, okay, you have a metric, okay, let's optimize that metric. Then the management is saying, okay, optimize that metric, I want 100% coverage. Okay, I don't think that's a good idea. So I'll show some explanation here. And really that's a very common interpretation. 100% coverage. Okay, tests are done complete. Ship it. No, I disagree. Okay, that's not so nice visible, but the point is more in the colors. Okay, forget the code. Just look at the colors. So I didn't want to present like a full coverage tool, but if you have templates, sometimes this works. So so here I have a template and template specialization, and here in the first part, it's no colors. Okay. And here, because I forgot to test the implementation, the specialization, so if I put this in Compile Explorer, oh, all of a sudden, I see there's something missing, something obviously, and here it's covered because the Compile Explorer is generating code for that, and that gets visualized. Of course, you shouldn't do that to use it as a coverage tool, but in this case it works and kind of illustrates how it would look like in your tool. And yeah, totally useful. I can see something I missed. Now, with templates, we have additional problems. Because template is instantiated with different types. So it might be instantiated for one type, but not for another. Okay, but you have only one line of code. And there are now different interpretations to how to interpret this coverage result. And so one interpretation is, okay, yeah, if it's templates, then of course this line has to be covered for all the possible template combinations. People are laughing, yeah, no, but really that's an interpretation that's used. And the other one is, okay, I'm relaxed, just if any template value is used there, that's fine. Yeah, I think the first interpretation is too strict. And in the practical systems, it's not reachable to really use that, especially if you have like things like Svine or funny specializations. You cannot practically reach that. And I'd rather stick to interpretation 2. So at least we should have that every line that we can reach is covered, and this our tool is showing us that we can do that. Okay, so here's the extreme example why if you need something to convince somebody that coverage alone is not enough. Okay, a square function, so from our first example, and yeah, it looks covered, okay, because Compile Explorer shows there's code for that. But what did I test there? No, I just called it. I just call it, and the coverage says, okay, it's covered, all fine. But I didn't do any check on the value. So that means the code is obviously executed, but it doesn't verify anything. Okay, and that's really strange. Shouldn't do that. So for me, the answer is, okay, just coverage is not enough. And this doesn't make sense. You can reach coverage without doing anything meaningful. So it's certainly a good tool. It helps you, but it by itself, it doesn't prove anything. Okay. Yeah, sorry, I just present too many negative aspects here. But let's step and do another step back. Okay, so what is a test actually? What do we want? And the picture that I have is, yeah, it should be, what is a test? It's some kind of filter. I have some inputs and the test says, okay, it's good or it's not good. Okay, so a good program gives me a green light, a failing program gives me a red light. So that's how the structure is basically from our tests. So we have input somehow in the fixture or in the equivalence classes, and then we get these lights. It doesn't make sense. So if I think it's a filter. So what's a filter? So filter something, I throw something in and I expect some things to pass and some things not to pass. Okay, so I have a new picture now. So I think what we really need is we have to treat the function itself an input to the test. Okay, I know which function I'm testing, and classically this function is integrated in this test thingy. But I think, yeah, it should be really a parameter because that's how I would test a filter. So I have to throw something in that doesn't come through, and I have to put something in that I know it comes through, okay? So I have two cases I have to check. So, and I just do that by supplying the parameter of the function as a separate, or the class, whatever, as an input to the test. Okay, and this gives us a possibility to check if our test is good, because that's what we're doing. The test is a filter. I want to test a filter. And this is how I do it. I have some things I know that have to pass, and I have some things I have to know that fail. And usually we're not doing that. We're just testing the good phase, right? So Okay, so the idea is to do some short selling of tests. So I have a test, and I say, okay, I don't trust that test, right? So I wouldn't buy stocks of that test. That's not good. So what can we do? If the function to test is a parameter, we can just go and provide some functions that we pretty sure won't pass the test or shouldn't pass the test. Okay, so we say, yeah, I want to see the test fail. If the test is not failing, it could be anything. It couldn't have assertions. It could be broken. It could be optimized out. I don't know. Okay, so that's the idea here. We want to have it a test that can be fail, and that we want to test it with some inputs, which are functions in this case. So we need some negative testing functions. So some functions or classes that we know will not work or should not work. So we expect those to fail. And what can we do there? Yeah, most of the time, empty function will not yield to will not implement the requirements that we have. Also, what we can do is just some functionality, just writing anything out, some constants, just writing zeros all the time, everywhere, or similar functions that have a different specification. So we can add parameters, we can remove parameters for those functions, and we can just write a small wrapper maybe to implement something that is clear that doesn't fulfill the requirements. And of course, if we have this infrastructure, we can just use old versions of our old implementations that we know didn't fulfill our expectations. So, and I came up with this name, adversarial testing, which really means to have an infrastructure in place to test good functions and bad functions. So, okay, so now I have to change the infrastructure a bit because I have to make the test framework work with that. It's really simple. That's basically all there is to it. We just have a template class and with one bool parameter. And if the bool parameter is good, if it's true, we don't change anything. We don't do anything. And if it's false, yeah, what do? We increment the count of how many times it failed. So also what we do is in the destructor, we do expect that there's a non-zero number of failures. So what's the reasoning behind that? So we assume that once this is passed, so the problem is if we test an adversarial case, some function that should not pass, we have to know that there were no failures. And we only know that after the test is through, so we need this guard to really check if there have been no failures, then of course the adversarial test is failed, right? Because it has to detect a failing, it has to detect the wrong function. Okay, that's it. And yeah, so as we have Google Test, we have some, and you cannot really change these macros in a nice way. So I just defined some additional macros here, and those macros just do some adding there of these called this guard object that we have to provide. And otherwise, if it's not in the good case, we just call the original macros. And that's it. And yeah, there's this little trick here. You know, maybe that for this expect macros, you can just use the output operator and put some additional information there. And if you do it like that, you can still do that. Okay. So sorting. Okay. Yeah, I'm just reusing my equivalence classes from last time. These you've seen. I don't need to talk about that. And so I have this test here. So that's really the change. We have to provide the sorting function as a parameter, and we have to provide the parameter that says, okay, this is a good test or this is a bad test function that we pass. And still we can use the types that we have. We're just testing some sort function, and we just have to add one adversarial guard here, which is one extra line of code. We use our equivalence classes from above. We have to instantiate the sorter, and yeah, we go over all the equivalent classes, and we say, okay, is it sorted? And if it's so, it's cool, right? So not a big change. We just have to add this guard, add this different macro. Okay, seems feasible. Okay, so unfortunately, we for our C++ version, we need some kind of wrappers here, but basically, we just have this, which we test the standard sort function in this case, because I don't want to talk about sort functions, just about tests. And so what we can do, so what I said, something that doesn't sort at all, actually doesn't do anything at all, we just put in here a non-sorting class that doesn't do anything. And also we can do just like reversing the input and seeing what this brings us. Okay. So what's the difference here now? So we have this infrastructure now in place, and here we explicitly just say, okay, we have still the normal cases that we should have before, and then we have adversarial test cases. We say, okay, we provide these functions that don't do sorting properly, how we need that, and we expect the test to fail. So this is really explicit. You see that this should not pass. Okay. Okay, and I run it, and oh, what's happening? So I would expect everything to pass, right? Because the adversarial test, the non-sorting should be detected. So, but let's look at the output. The number of failures is not 0, so it means it is 0. And so let's see which case this is. So here we see it's the non-sorting one. In the chart with the char, so if don't sort it, it's still sorted. So how is that? Let's have a look. What did he do wrong? Okay, we found no failures. So let's see what's going on. Nothing has changed, and this passes. Yeah, the inputs from our tests were already sorted. So everything was sorted already, and of course that's silly. But I mean that happens. So it might have the input data, the values that you want to test might be inappropriate for testing, right? Okay, so I mean that's easy. Just add something that's not sorted, and then it passes. Okay. Okay, we can do. I'll try to do this online. This is really satisfying if I can make it work. Because that's really kind of the trick here. So we start here. We are in this failing case. You see this is failed. You just, oh no, failed. And so the only thing here actually that you have to do is just to provide some, let's see if this works. So what's this doing? Okay, great, it works. So we have to provide a new my vector with type, and with just something very simple that just is not sorted, right? Okay, so I don't see that properly. So what's the point here? Okay, yeah, it's hard to see here. Okay, let's see. Okay, great. Thank you for debugging. Okay, and of course I have to here because I just use plain arrays. I have to fix that too. But, come on. Probably now the internet breaks down. No, it works, it works. So here, everything passes, all the tests pass. Yay, we did it. So cool. So we just wrote some code. We used some empty code actually. And it showed us some defect in our tests. So let's do more, okay? So we've seen a similar, the function from before. It was to illustrate that you need requirements. Here I try to give a better name. So generate sequence from first. So here I have to deal with a special case because it's empty. We have empty inputs. We have to deal with that. But basically the same function from before. So let's put that in. Okay. Okay, we can show this online. Maybe that's also more fun. That's definitely more fun. Here, okay, so I have prepared that. So the only thing I have to do here is add these cases. So okay, can do just add the reverse. Let's see if this makes something better. No, probably not. So reverse doesn't, wait a minute, should still compiling, still running? Should be for tests, yeah, for tests, no change. So, okay, so that didn't reveal anything interesting, but let's have this one. And what's going on now? Come on. Oh, wait a minute. Oh no, another failed test. Ah, damn. Maybe, but actually that's what we want. We want the tests to fail to see if there's something going on. So what's going wrong? Okay, let's look at what is the test really doing again. So the test is really just testing. Is this thing sorted? Yeah, of course it's sorted because it's generating a sorted sequence. Okay. So how can we fix that? So I've prepared this one. So how can we fix that? Basically, what we need to fix our tests. Okay, it's on the slides. Okay, let's see. So we fix that here by just adding another test. So what do we expect from sorting? We expect from sorting that the old elements are still there. So what we only have to do, we copy the data that we want to test, we sort it, and then we just have a small loop checking that the items of the old element are still there. And once you have that, it passes. Okay, so what we've seen is we have really a way, just providing silly functions to ensure that the test is really appropriate. So the second part that we checked for the copy, that's something that people might miss. And here we just use a very simple function to show that the test is not appropriate. Okay, what we should not use as test functions is if it's like really randomly behaving, if there's calling some random function, random numbers, that is probably hard to detect or might not even produce a failure. Also, if I try to force undefined behavior or try to invoke that, it's probably not good to do that. It might be possible if you have like sanitizers, but I wouldn't recommend it. So also what's shouldn't be done is something that's not in the part of the requirement, and this is the same, has the same effects. Like you could also use stable sort. Should also pass. You shouldn't use that as a negative example. Okay, so why I think that this is a good methodology. If you use it like that, you will get a better, you'll find your bugs earlier. The tests will automatically become better because they're shown to detect inappropriate values. If you can provide these inappropriate functions also to testing, so they know what to detect. So it's kind of painting the negative space. You don't say, okay, this is what's happening, but also say, okay, but you should absolutely detect if something like that happens. And this is something that we didn't have before, basically. For the testers, why should they care? I mean, probably they will have to come up also with negative examples. So as a tester, you can think of it that this is this methodology, the adversarial testing, is really the way how to test your unit tests. So these are the tests for the tests, and this adversarial testing can be a testing of your test, right? So what we also seen before, the test becomes really generic because the algorithm itself is just another parameter, and you might reuse some aspects that you're testing also for other functions. So then when you might just consider, you might have different kinds of sorting, bubble sort, quick sort, merge sort, and you just basically have run tests. Why would you write multiple tests for that? And so you just pass, you just have made your testing automatically better because it's kind of part of the design of the tests. And yeah, you can test equivalent implementations. But let's say what often comes up is the discussion, okay, is this test good enough or not? And if you have just one positive test, it's really hard. So typically these discussions go like this. Yeah, I think that's okay. And I don't think that's really covering everything. So I'm not so sure. I think you should test more, but I don't know what. And this really turns out in the philosophical discussion. There's all kinds of testing strategies and philosophies around there. And I'm not so sure. And with this approach, all the failures are concrete. So if it doesn't work, you get an error from G-test, and you know what to do. So there's no philosophical discussions. Everything just fails if it's not correct, or it passes if it's correct. And of course, you can express your expectations. You just don't paint the positive part, but also the negative part. So, it's often very easy to have these examples, and you can put them in the review comment. Okay, look, nice test, but I think this case you wouldn't catch. And then you can try it out and see, yeah, okay, right, you're right. So I changed the test. Okay, another point, we're in the age of AI. Not all the tests that are written and will be written by humans. So we have AIs to help us. Oh, cool, great. Yeah, but how do we know that the tests are good? I mean, that's my question here. So and we have some kind of partial solution here. So that means the developer in the future will just generate code. I mean, that's what developers do. And the AI will do the testing. Okay, nice. But now, how do I know the test is good? The AI might fantasize something. But now I have a possibility to test it. If the AI is generating rubbish, okay, I just generate an adversarial implementation, and the test will not work. And I can say, hey, look, no, that's not what I wanted. It doesn't. The result produced by you is not good. And of course, I mean, because you just need really stupid functions, you can also let them generate by the AI, and it doesn't even have to be good, right? So you just have to compile. And if you ask the AI to implement your program and it's not really working, don't throw it away. Just keep it, and it will give you an improved test. And if it's successful, yeah, also nice. Then just tweak the specifications a bit, and it will produce something that will be useful as an adversarial test. Okay, so I assumed some questions. But is more work? Yeah, sure. I have to come up with these negative examples. I mean, if you use this approach, you have maybe to do some of this wrapping of these functions. If they are functions, or if they're classes, you have to write whole classes or something like that. Yeah, it's more work, definitely. But if you don't do it right the first time, you'll do it twice. And maybe the error just appears in production. So it's always better to have good tests before. And one of the main ideas of test-driven development is really to start with a failing test. And I say, why start with a failing test? You should always have a failing test, but just with the right inputs. So once you have a failing test, you should make it part of your test concept. You can use that. This is really important. Yeah, so some machine, I don't know what's the correct word here for some AI, might do the work. I haven't tried that yet, how this turns out. If I say this is a new test idea, let's find out. Yeah, another point that I expect from my superiors. Yeah, so we have 100 courage. What are you still doing here? Why are we doing that? So yeah, of course, we've shown courage is not the answer to all my questions. but we really have to, the test must be able to find an implementation that is not appropriate. And this is how I can show it, and this gives me a good feeling about the code. Yeah, coverage is really, should be required, but by itself, it's not sufficient. That's that. Okay. We're not done yet, not quite yet. So I have presented this methodology. I think it's better than what we did before. Yeah, but still maybe there's something, still not working. So how could we do that? In AI, in machine learning, there's this idea of holdout set. Okay, and this holdout set means I do the training and I do my work with some set of inputs, which I know are good or bad. I mean, this is really matching to this method here, but I really don't do that all the time with all the values that I have, all the inputs that I have, but I have some set that I also know the answer of, but I don't put it to the test. So this is something we can do. If we have enough time, we just hold something back, and you can maybe something that's really complicated to do and can put this into some special step to test it. So there's this idea of mutation testing, and you might say that this approach is like manual mutation testing. Okay. So the idea here is often that you have a framework that somehow magically changes your implementation. And for me, that's not controlled enough. So sometimes you can change the algorithm, you can totally change the structure, you change a single operator, and it turns out it still works. Maybe it's less efficient, but that doesn't prove anything. And if it's useful, I mean, do it, but I think it's not useful to test the tests. Yeah, what you can always do is look at some higher level metrics, because you will see number of returns or number of complaints, tickets, whatever, will show you probably if your method is good. And of course, ideally, you would do some kind of double blind test where you have like 2 teams, 2 products, and one is using this method and the other is that. So that's how we could verify if this really helps. I haven't done that. So if anybody has the time or the budget, or that would be really cool if somebody found out. But yeah, so that was my idea, and I will feel more confident with this. This is really the first proper idea that I came up with that has some teeth. As I said, coverage is too weak, and we didn't have anything else actually. So with this, I can rest assured. So another example that I have is at the airport. So I came here by plane, and so you have to put your bags and on through the screening. And how do they test that this works? Okay, they look at stuff all the time. They might not just find something that is dangerous. Okay, they find all the water bottles and so on. Okay, that's okay. So what I heard is that they sometimes have checks, people coming, having some fake weapons, fake explosives, whatever, they put on purpose, and the people have to find that. So, and this is kind of the equivalent. We have to know that the system is able to find the thing that's supposed to find. And this can help us really to ensure that the method is really helping us. And yeah, that's all I have to say for now. And now I have another conclusion, obviously. Okay, so another big conclusion here is we have these equivalence classes. And I think if you structure it the right way, it doesn't have to be the way I did it. Maybe for your use cases, it looks different. But I think it's important to have like a good definition, separation between the testing infrastructure, basically, and the data that you're testing. And the important thing with that is we can improve the quality of tests with that. So we've seen the examples. if you add just very stupid functions that really improve the test. So that the functions were not hard to write, they were not very complicated, but they showed some defects on our testing. And if our test is better, then of course our code will be better by design, right? No, by necessity, right? So we have a test. If the test is better, we're bound to get better code, and that's the idea. Of course, with AI, this has a big potential to really check the AI output. If the AI output produces code, okay, I have to write tests. Okay, and if the AI also writes a test, what can I even control? But if we let the AI write the tests, we as humans have a possibility by rather simple examples to really double check if the test that is produced makes any sense. Okay, now I have some thanks. So many thanks to Matt Goldbolt for Compile Explorer. This we saw that in the live demo, and I think it's a great tool. If you don't use it already, please do. It's great, it's life-changing. Then I used for the slides here the MARP framework, which is basically you write this in Markdown and you get slides like these here. Then, of course, ACCU for providing this possibility here, and these very nice conferences. Also all the people attending ACCU for inspiration and ideas for this talk. And I want also to thank my team, which also came up with many of ideas for this talk. And also Reza Ahmadi, he teaches me a lot about testing stuff and responsibility diffusion, which is another nice topic, which we can't handle here. And of course, the Dan community at Bosch, which is the developer advocate network that really is caring about the developers and giving them the right tools and incentives to work. Okay, but now it's time for questions.